let's see, we can go ahead, Danielle, we can, yes, okay. So, and we are, this is it's going to turn into a bulletin that is one of our sort of physics project bulletins. The theory of these bulletins was supposed to be they're quick, they're short, but they're turning out to be definitely not short and not quite so quick. Okay, but so this is a bulletin about multi-way systems based on numbers. And the idea, so first question, can people, I have a big screen and I'm assuming people can see things at this resolution. If they can't, I can make it bigger. It's convenient if it's at this resolution, but people should just complain if they.
I'm on a 10-year-old laptop. It looks fine to me.
Okay. All right. If Ed can see, then it's all good. Okay. So let me just review what this is. And so multi-way system. Everybody kind of knows here what multi-way systems are about. The idea is to look at multi-way systems that are in which, and I did this, I had a little comment about this in NKS, and in fact, one of the more interesting such systems I actually had discovered in NKS, and let's see, if I go here, so 0, 4, so I just want to make sure that everybody understands what these things are before we keep going, or this is going to get very silly. Okay, so and actually, we one of the things that I had asked for, and I realize I'm not sure if it's been produced, is a modification to. Okay, so let me just explain what this is, right? So at every step, n, like 0, can go to n plus 2, goes to n plus 2 and n plus 3. Okay, makes sense? So 3 goes to 5 and also goes to 6 there. Okay, sometimes they merge, often, usually they branch. Okay, everybody's on mute, but you can please speak up if you have something to say or whatever, or it's going to be very okay. So let me see. So we had a new function repository item that let me just see where it is. Multiway function system, which I think was I thought it was called Multiway. Oh, I spelled it wrong. I still spelled it wrong, although I have to say that this should support spell checking better. Okay, so let's look at this here. Let me just use the rules that I had got up here. That arrow thing is a nice version of a notation for our function object. Okay, so let's do this, 0, 4, get rid of that. And hopefully this is going to be, okay, well, it looks more beautiful. The one thing that it isn't doing right now, which I had thought it was going to do, and maybe who's on here who could text Jessica and ask whether this was done. I'd asked that there be a way to label these edges to say which rule was applied. Maybe we could find out. Danielle, are you able to do that?
Yep, I was just getting a screenshot so I could point to it.
Okay. Boy. Okay. All right. So, but people understand. Okay. So let me go through what I was actually doing here, and I should probably actually use this this version because it looks nicer. There. You know, I will say that this is see what that looks like. Okay, fair enough. Yeah, all right. Anyway, so I will replace those in due course. All right, so there are questions about how things work, and let's go to something exciting to begin with. Let's see, I was just starting to look at, so these are different cases. So this is if you do n goes to 2n, n plus 1. Let's actually make that with our new version here. Let's say see whether that looks reasonable. Oh, great. That's disappointing. Well, that looks terrible. What did that just do? Oh, I see. I wonder what I did wrong here.
Statey.
What's that? Oh,
State.
statey. Thank you. That. No, states. Oh, states graph structure. Much better. And now I want the layer digraph embedding. Okay, that looks quite beautiful. Okay, so this is a slightly more complicated case where we are mixing addition and multiplication. But what I wanted to look at, okay, great. Again, we got some housekeeping to do of updating the graphics. Let's take a look here. So Ed, by the way, I think you had looked at this case here, hadn't you? And did
Yes.
you see something out about that?
No, I didn't.
Okay. 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 Well,
I think it's basically of Collat's variance.
right. So this does. That's weird. Okay, that's an attempt to. I need to explain what's going on here, but well, let's see. Well, let's go to something more exciting to begin with.
Before you get started, I got a response from Jessica. She said it's not done yet. Jan looked at it, but said he needs Jonathan for it, and you have Jonathan hostage at summer school.
Oh gosh, that's not good. That means I get to do it myself. That's not good answer. No, he doesn't need it. If he needs Jonathan, Jonathan can just do it.
Okay, I'll let him know. Thank you.
He needs to actually do it. Okay. So again, where should we start here? I'm just trying to figure out where to get started on this. Let's look at complex numbers. That's a good case. Okay, so remember what we're trying to do is we've got we got some rule, and that rule is, oh great. What? Why didn't that work? Oh, I see what's wrong. Sorry. Okay, so let's take a look at what this is. Oh, there's another problem here. Okay. I'm not, okay. Actually, I had looked at this with some kids, some of whom might be on here because I invited them last weekend. Let me take a look at what I had figured out there. See, this is a never do your homework on your own if you can do it with other people theory. Hold on, let me just find what I'd done there. Let's see, this was June 21st. Okay. Oh yeah, we were looking at powers as well. We started looking maybe at the complex number case. Yes. Okay. There's several different things here. Sorry, this is rather disjointed, and yeah, that was interesting. Okay. Yeah, there are a bunch of different cases here I was going to look at. We could look at complex numbers first, and then we want to come back to some other things. Okay, so let's look at complex numbers. So this was looking at, let's take this case here. So what's interesting here is that if we, so we're looking at n plus 1, n minus I. Let's look at n plus 1, n plus I. Then what should happen is, yes, we're going to get something like this. So let's do this and say here, vertex labels. So this is essentially a coordinate grid. Placed automatic center. Maybe I don't want that. I just want automatic. Okay, so, oh gosh, it's upside down. Okay, so it's okay, so the whole point is here, 1, let's start off from 0. Okay, so we're starting off from 0. So this is basically making the standard, you know, if we got rid of the vertex coordinates here, this thing would look like our other trees. Make sense? But in this case, because we have complex numbers, we can actually associate this with particular coordinate positions. That make sense to people? Somebody's got to respond. At least Ed. If nobody else, at least Ed can say.
It makes sense to me.
Okay. All right. Okay. So okay. So we're, you know, with these complex numbers, just grows that kind of tree. So the question is, and we have, okay, so let's try looking at what happens when we use, if we, so this was a case 1 plus I, n plus 1, okay? So, so that's when we, so in general, we can have A times n plus B, C times n plus D. And the question is, what will that do? And I suspect that in some limit, that is like the world of, I forget, Fuchsian groups or some such other thing. Maybe somebody knows. And what that will segue into is the story of, I think I had put that someplace here, the story of complex numbers where we are looking at, so in this case, let's take a look at this and let's compare these. Okay, so this is a case where we're taking at every step, we are, and this is kind of messy, right? Because this is taking the complex numbers, and I think there's a mapping that's similar to the previous one we just used that makes one of these standard kind of branching tree things. I had a bunch of these in NKS that were, I think this is probably an example. Well, this is an example that shows with non-integer complex numbers, shows the location, shows what happens, right? And the first one thing we would like to do is to compare what we get for this. And one person, yes, somebody is sending me a chat. Ed is sending me a chat message with, what is this now? What is this, Ed?
That puts things at their complex coordinates.
I just had that. I mean, I have that
okay.
up above.
Okay.
But yes, that's useful. But now the question is this thing that makes a tree. Okay, so for example, let's see, where is this is Banat, former summer school student and now person working on a project with us, but he's done a lot of work on these trees. On the case of so he has looked at this, and I would like to connect what I'm trying to do with what he's done, and this is also related to what was in the NKS book. So in the NKS book, bizarrely in the section on plant growth, I had a whole discussion about these kinds of trees. Okay, and in particular, so why do we care? One thing that happens with these trees is there's a question of, do their branches rejoin or not? Do they have some kind of causal invariance? In particular, what's interesting with these trees is that these are real number, I mean, these are complex number, continuous complex number results. And the whole idea of causal invariance and the whole idea of the remerging of branches, I'm trying to understand what the kind of continuum version of a multiway system is. See, an ordinary multiway system, right? When we're doing something like this, we know that the 5 branch and the 4 branch, they actually both go to 7. But if these were real numbers, chances are they wouldn't, go to the exact same value, except in some limit, if that makes sense to people. So, anyway, so my question for Ed or anybody else, so the way these trees work, so Ed, do you understand how these trees work?
Yes.
Okay, so then I want to know the answer to the following question. What, how do I get, using this kind of multi-way system setup, how do I get something analogous to those trees? Do you see what I'm saying? I mean, so in other words, what is the function that corresponds to one of those trees? What's the multi-way function that corresponds to one of those trees?
Right. I'll think on that. Some sort of multiplication by a smaller value. One thing you see with these complex numbers is because they're so low, it doesn't grow very fast. If we used even smaller numbers, the actual coordinates would go to that sort of tree growth, I believe.
Okay, well, let's just try that.
Something smaller than 1.
Let me just store this in the right place. Okay, so your claim is that if I look at this, so let's define this as, let's just call this, let's define it as just complex multi-way. And I don't know, do we want to, this seems relevant. Okay, hold on. Complex multi-way, so let's just define AB, let's just make list pair AB CD, and we want to go init, which will take by default to be 0, and T, an integer. Oops, T, an integer. Okay, so let me just fill this in. A, N plus B, Cn plus D, init, and T. Oh, you know what I want to do there? I want to put up an options. I'm going to be lazy and just do that. Okay, so now we say complex multiway. So Ed, you have a speculation here that if we use a number, something less than 1 here, is that right? Ed?
Yes.
So what are you suggesting?
Oh, well, 0.9 and 0.8 for the second. 0.9.
No, but what should B be?
0.1 I.
Okay. C?
And 0.8, 0.2 I.
Okay. And let's say 0, let's say 4 steps. Okay, that didn't work. So those are all, why is that? Is that because that's all real parts? I mean, is this?
Oh, try starting with 1 instead.
Oh, wait a minute, that looks more promising. And you think we should start with 1?
Yeah, I think we've fixed it.
Yeah, I think by starting with 0 there, oh gosh, why are those points so big? Why is that so crazy big? I don't know why those points are so big. Okay, so now the claim is, why are those points so big? That's just crazy.
Oh, because we're staying close to 0.
Oh, okay, well, let's say vertex size, arrow 0, what would happen then? Then we have giant arrows. Brilliant. Well, okay, fine. Okay, so maybe what we should do here, why are we staying close to 0? Go ahead.
Did you see the chat from Nick with the resource function code?
Yeah, let me look at that. I think that resource function code is actually, okay, well, what do we do to plot that? Endpoints, that's, so that's just looking at, that doesn't look promising. Why did that go wrong? Oh gosh, we need point size there, plot style. Okay. 0.05, okay, let's try like 7 steps. Okay, fine. So that is giving us, that's the same type of idea, but that's giving us the endpoints here. So here, let's look, I mean, for example, let's look at the map that we have in the NKS book, which gives us, this is a complex, this is 1, and then we've got a complex number and its conjugate there, I think. So let's say we go to, I'm going to guess that might be 1.5, and then 0.5i, and then there 1.5 minus 0.5i.
Right. One thing to consider is basically keeping with points that are within Mandelbrot's limit.
What the heck happened there? That's crazy. Okay, so what are you suggesting?
Basically, values over 2 are risky because they'll explode, but things under 2.
Okay, this is clearly wrong. Okay, we got to figure out something. This isn't right because this is multiplying by. Let's try to understand what the this is again crazy. Okay, let's just try to understand what this is doing relative to what this is doing. Okay, so in this case, implementation of the branching model. So this is saying outer times of 1 plus hash sign. Okay, extend from the point, we can take the original stem to extend from the point -1 to 0. Okay. Rule is then specified by a list of complex numbers corresponding to the positions of the tip. So this is taking at every step a multiplication of 1 plus hash sign. Hash sign is the current set of numbers. 1 plus the current set of numbers times the new numbers, right? That makes sense? So
Yes.
each one of those, so that means it's 1 plus that, 1 plus z, where z is the current thing, times, and that number, there's a pair of numbers there, which is some number, I don't know, we can call it c and c star, right? That makes sense? No? Yes? Maybe? Okay. Do you understand what I'm saying? Anybody?
I'm trying to type something.
Okay. Well, okay. If anybody else wants to respond, please just speak up.
Yeah, and if
Yeah.
anyone's having a hard time unmuting themselves because of the way this is set up, if you have a raise your hand function, I'll see that and I'll unmute you. Sorry.
Yeah. Because, right, okay, so one thing we're trying to do is solve the question of how do we get these complex number trees there. But another thing we can look at is just looking at this complex multiway thing, and let's just look at, for the integer case, let's just see what happens if we just compute it for, well, now we've got a big range of things to look at here. So we could say, let's look at A, B, we'd really like to look at a whole grid of possibilities. Let's go from -1. I have this terrible feeling I've already looked at this. From -1 to 1. So let's say for each of these numbers, A, B, C, D, we can make them range over, I mean, we could take some examples here. We could take -1, 1, I, minus I, 1 plus I, 1 minus I, let's say. Okay, so for each of these, we can I hope this isn't going to look too stupid. I mean, this is going to okay, so let's do this. Let's say outer that, and we're going to go, this is rather an inefficient way to do it, 1, 2, 3, 4, level 1. And then I want to label this with probably that quantity there. And am I doing this right? I know we have plenty of experts here, so just tell me if I'm doing this right. What we probably want to do, well, I should have probably done this in parallel across a bunch of machines. This is going to be too slow. No? Okay, there we go. All right, so this is our map of some of the behaviors we can get. Okay, somewhat complicated. Now, I don't know whether these are, so this is this complex multiway thing where I'm using the vertex coordinates from, I'm actually using the correct complex number of vertex coordinates. So something like this, maybe we can try running it. I'll tell you what, why don't I do this? Why don't I say, rather than this, I think we had more. Okay, so we got quite a range of different kinds of things that can happen here. We could pick some particular examples and try and look at them in more detail. I mean, the goal is to try to see, I mean, some of the structure may be confusing because it may be just because, I mean, looks like some of these things have a grid and then they have some other behavior. So for instance, let's take that one. Okay, so if we go, let's say, go 10 steps. Okay, well, that's a lovely looking object. Let's say, instead of this complex multiway thing, let's have a version of that, let's just call it complex multiway 0 or something, which doesn't have the vertex coordinates piece. And let's see what happens if we do that. I mean, okay, again, I probably didn't motivate this very well, and maybe I should try to do that. Okay, isn't that interesting? So that looks very much like what we were getting some of these other places up here. But now, because we have these coordinates, we're able to see how this is laid out in actual complex number space. So this thing, so I wonder whether we can, maybe we should take a more minimal example. Anybody got an idea for a more minimal example of this? I could probably look at the map here.
I'd say just a random case with more random complex numbers. I sent something in chat.
I don't think it's a good idea because as soon as we have non-integers, we will not be able to, we will not get, okay, we can try that, but you know, this thing here, notice that this thing here has a lot of things that rejoin, right? So I mean, if I were to do this, if I were to take this thing and I were to say, let's say 7 steps or something, and I were to say layered graph plot, okay, what we see, hopefully, is that many pieces, well, it's not as convincing as it might be, but let's try like 8 steps or something, 9 steps. Okay, so what we're seeing is some things are rejoining, right?
You can also do that with algebraic numbers. If, like square root of 2, if they're simplified, I'm not sure if they'll collapse if they're not.
No, they won't if they're not. But yeah, I agree with you. I mean, if we do the same, I mean, anything, you know, this is some property of some number field somewhere that allows this to happen. So, you know, one of the things that we would like to be able to figure out is when is there causal invariance, when it's not. Okay, let me try and motivate this a little bit better, okay? So let me tell you what got me into looking at multi-way systems based on numbers. The question is, what is the continuum limit of a multi-way system? Why do we care? We care because in the actual universe, the multi-way system that we're dealing with might have 10 to the 120 branches. That's a lot of branches. That's enough branches that one would like a continuum description of it. So the question is, what kind of object or space is the continuum analog of a multi-way system. And so what I was thinking about was these complex trees as a possible example of a continuum limit of a multi-way system. And the problem is, one of the most important properties of multi-way systems is causal invariance, and it was unclear to me how causal invariance would work in the case where one has. Actually, I'm going to ask a question because I noticed that Phil was on here, so I'm going to pick on somebody. In the world of binomial trees and people doing simulations of things like that, are they anything like this, or is that a completely different story?
I don't think so.
So that, sorry, we didn't. It was hard to hear. Oh, yes. Okay.
This is Barbara Mack, and I could just make one comment on that from Quant Finance. The trees are much less complex than yours because it's just a binary decision. The stock, at its simplest level, the stock is at 0 today or 1 today, say it's going to go up or it's going to go down. So your trees can go out day after day after day, but the changes as perceived in these very simple models are just up, down, or sideways, really.
So what you're saying is those trees are just basically a thing that looks like this.
They're very neat and organized, like your lower, the third one there. Yes, exactly.
Yeah, okay. All right. So
there's a real problem in quant finance with jumps, and we could get into that sometime, but that's where it gets complicated.
Fair enough. But so when people talk about evaluating a binomial tree, they're literally just thinking about it like Pascal's triangle, so to speak. It's not there's nothing more complex that so it's nothing like these. Fair enough. Just thought I would ask. Okay, local volatility, Phil says, could change, but that's about it. All right. So it goes. Okay. I mean, always try to leverage some other area if one can. Okay. So anyway, so the question here was, when we look at, let's take a look at some of these things up here, like this case here, right? What's the continuum limit of this object here? What's the limit of that object as number of steps goes to infinity? I suspect in that particular case, it's a hyperbolic space. So I don't know, we can do 16 steps or something. And one thing we could do, so this has the property, if we start at the center here, the number of things that we reach going out t steps rises like Fibonacci of t. Actually, a good question here, which I don't know the answer to, which we should answer, is if we don't take, actually, here's a good question. So if we take this and we don't start at the origin, we start somewhere else, is this always sort of an exponentially growing space from every point? So what we would like to do is to say, I think we have a resource function called graph neighborhood volumes, if I'm not mistaken. So what that's going to do is it's going to take from every point, it's going to work out. Oh, look, it's using all my parallel machines. That's nice of it. What it's going to do is it's going to start from every point here, and it's going to grow this kind of geodesic ball around that point, asking how many distinct points can you reach by going n steps out from that point. Oh, baffle. Look at that. You see, I have 100 CPUs in my house, and it is unbelievable how often some random CPU will not come to life. Okay, there we go. All right, so these are the results. So this says for every node, this says the growth rate. So what we can do here, I think I can do, if I say something like resource function of ragged mean, I think that will give us values of this, if I'm not mistaken. Ragged mean around. Argument that is not O. Oh, well, okay, let's try. Sorry, what I'm trying to do is to average these. Okay, this is something very useful, just got posted on the chat. I think I need to look at documentation for ragged mean around. Oh, okay. What did I do wrong here? Oh, just need to say that. Okay, hopefully I'm going to get this in a moment. There we go. Okay. So what this is showing is, oh, that's really weird. So that's showing the, for this object, okay, so what that's looking at is, given this object, starting from different points in the object, what is the growth rate? So this looks like it is behaving like a one-dimensional object here, because it's only rising. The number of things that you reach going a distance r is only rising linearly, which is really weird. So I think the thing we want to try is to do the same thing for, let's try doing it for like 14 steps or something. And let's say, so this is now going to generate, okay, great. Okay, this is definitely odd and not what I would have expected, because I would have expected that this looks to me like a you know, some kind of hyperbolic space where it has an exponential number, because if you start from the center, the number of nodes you reach goes up like Fibonacci of t. But apparently that is not the case for if you start from other points there, which is really surprising to me. And I guess what we should do here is to look at the log differences, because that gives us a way of estimating the dimension. Was percent 61. Okay. Okay. Not what I would have expected at all. So this shows that there is, in terms of the, this is showing us the growth rate in the number of nodes you reach. So if this had been a tree, like let's consider the case 2n, 2n plus 1. If I were to do 2n, 2n plus 1, let's try that case. Let's not go as many steps. Let's say 12 steps. 2n plus 1. I claim that as a tree. And now if we do the same computation again, let's do this. So let's say, let's put all of these together. Let's do this. And then let's say log differences. Oh, I could have done that actually. And then I'm going to do a list line plot of that. Log differences of this. List line plot. Okay, so that, if we look at this, this is growing exponentially, because we can see the effective dimension, which is what this is plotting, just grows like that. Unlike this case, where the effective dimension seems to go to 1, which is not really what I had expected. So in other words, if we were growing this like a, so for example, in this case, this is 2n plus 1, 3n plus 2. So let's try that one. 3n plus 1, 2n plus 2. That's odd. Did I get this one? 2n, oh wait a minute, 2n plus 1, 3n plus 2, 2n plus 1, 3n plus 2. Aha, okay, so look at that one. That one is asymptotically going to 2. So if we run it for a few more steps, let's say 14 steps here. Okay, so this is kind of interesting because it's similar to what we've seen elsewhere. That this is, okay, so this is like a two-dimensional space. This is making an exponential dimensional space. This, to my surprise, after an initial transient, is effectively making a one-dimensional space. Now I assume, so somewhat surprisingly, we're getting very different things there. And now, okay, all right, let me try this code that Nick put in the chat here. So this was nested branching graph. Okay. So the idea here, I guess, is this is analogous to the code that was in NKS. So nested branching graph. Okay. All right. Now, can we turn that into? So my question is, how do we relate that to this just pure nest graph thing that we were doing? What is the function that corresponds to this? So what this is showing, somewhat to my surprise, is that there is convergence between different orders here, different paths through the multiway graph are winding up at the same state, which I have to say surprises me, because I would have expected that with, oh, well, maybe that's just an algebraic fact. Maybe that maybe it's because of the construction of this, which we don't. If we knew what the function was, it would help a lot. So, okay, so let's go back up here, because what we were discovering here is that, again, a question would be, what is the large-scale limit of this object? To what extent, and for example, is there causal invariance in this object? And we can actually test that, because we could actually say in here, our multiway, that multiway function system thing actually has a causal invariance tester in it. So for example, we could test, let's just give an example here, and this is getting to be a really messy notebook, which I'm not happy about. Okay, so multiway function system, and we're saying the rule is n function goes to, and let's say we are looking at that that one that gave the Fibonacci stuff up there, 2n and n plus 1. Starting with 0, and let's go 3 steps, and let's say causal invariant Q. Oops. Okay, so that one is claimed to be causal invariant. So let's go 5 steps, check it again, it's causal invariant. So that means, remember, causal invariance means every time it branches, it merges again, okay? So for example, we can look at this one here, and we can ask whether it's true of this one as well. And this one, we've got A, B, C, D there, so the actual function is, let's see, we've got A is that, plus B is this, And then we've got n plus 1 minus 1 plus I. Okay, so let's see what this says about causal invariance. Okay, so that says the least at 5 steps that is not causal invariant. So that means that in that case, there isn't as much merging as branching. We can just try, I'm just curious whether at different numbers of steps, it's still false. Okay, let's try 6 steps. Still false. So what this is asking is we go up, I mean, in general, it's undecidable whether, there's no upper bound on how far we have to test. But this is asking if we allow it to go more steps, will the thing eventually converge or not? And this is saying it doesn't eventually converge. So this is not, in this case, for that set of parameter values, it's not causal invariant. What I'm guessing is that in some sense, in the real number case, there will be domains where it's causal invariant and domains where it's not. And I think that will be interesting to see. And what we are seeing in, let's see, in Bernat's work, and also he had a better version of what I had in the NKS book, where he's looking at, this is questions about whether the tips rejoin or not. So, and again, please ask questions if you guys want to know what's going on. So the issue is he's got these trees, and the question is, does, the different tree branches correspond to taking different values in taking different branches, because he's got pairs of complex numbers and he's going, one branch takes, like he's labeling the complex numbers 1, I'm guessing that, 1 and 2 here. And so he's saying that 1, 1, 1, 1 followed by 2 recurring is the same as 2, 1, 1, 2 recurring. Does this make sense to people? So the whole point is that in this case, he's looking at the infinite limit of taking the 2 branch at every step. So a bunch of 1 branches and then the 2 branch thereafter. And that infinite limit is the same as taking the 2 branch, 1, 1, and then the 2 branch thereafter. Does that make sense? So unlike what we're doing here, where we've got integers and we're taking only a finite number of branches, he's got complex numbers, continuous complex numbers, and he's taking an infinite number of branches. Okay, but the issue is that you can probably still define a notion of causal invariance for that infinite number of branches, and that gives us some idea of what the what the continuum limit of these multi-way systems is. So let's see, we had another suggestion from Rick. Yeah, I understand that resource function was made quite recently, and I think it was just made from that NKS code. The question that I'm asking is, how does it relate to what we were doing before, which is to just use nest graph, right? So down here, if I wanted to, where is it? Instead of using wherever I had it, here, I could literally be saying, right? I could be just saying nest graph of this, okay? And the question is, what function can I be just nest graphing to get the same result? Okay, so that's giving the result that I was showing above here, right? That was a different number of steps. So if I go to 10 steps, I'll get the same result there. Right, so the question that I'm asking is, in the case of these trees with a particular value of b, what is the precise analog of just saying the value n gets mapped to some pair of values? What are those precise pair of values? That's the question. Okay, and what I'm trying to do, look, I'm going to, partly because people aren't saying things, and I really wish you guys would speak up. I'm happy to hear from anybody here. What I was going to do was trying to systematically look at what happens. Okay, I'm gonna just do what I was going to do. So I'm going to, I'm afraid, pretend you guys are not here because I'm not hearing anything. So it's very difficult for me to do anything else. What I was going to do was I was looking first of all at integer. One of the questions was, under what circumstances do integer versions of this, where you're just adding integers, when do they join and when do they not join? So so I looked at the case of just adding integers here, and it is the case that for any pair of integers, oh, actually, wait a minute, this is a better case. Yeah, actually, I'm sorry, this is the case. I'm looking here at not pure multiplication, multiplication and addition together. Okay, so the question is, what do I get here? Do I get and what I was looking at here, let's see. Well, I'm going to add to myself for myself here. I was trying to keep this organized. Dear, oh dear. And this is what I get for leaving this from Sunday until now, because I've forgotten how. Okay. Let's say, okay, I'm going to make a section here called I'm trying to remember what I had done here. So, oh, that's the, yes, okay, so this is the causal invariance case. Well, I'm going to do this at least approximately here, and then we'll do it more exactly. So I'm going to say, I'm not exactly sure what this is going to end up being, criteria for causal invariance, but I don't think that's quite right. And what I'm looking at here is, if you look at this, this is asking, what is this doing? What on earth is this doing? This isn't right. Okay, I'm sorry, let's look at this case here. This is asking, given a particular one of these systems, A, B, C here, we're asking, if we look at this mod C, let's take a look at what we need to look at here. All right, what does this mean? This is asking, given a particular initial condition, can we ever reach? Okay, so one way to determine what values we can reach is to look at all numbers mod k. Okay, so let's just to keep this consistent, let's call that k. And so what this is now doing, so then what we should write out here so that we understand what we're doing is we should write, let's just write that. Okay, so I'm going to go to value, let's say 3 here, just so we see what's happening, and then we'll do it for the more real case. Ah, stupid, sorry. I want that mod k, and that also mod k. Okay, so what this is showing is if n goes to, I wish I put the mod outside the whole thing. I want to put that mod, I'm going to do something very hacky here, and I'm going to put a hold form in there, just so that it doesn't, wow. That's wild. Okay, somebody give me a better way to do this. Let's do this. Okay. All right, so this is showing us, this says if n goes to, and I want to make this smaller because I don't want to, okay, so if n goes to n 1 plus n mod 1 is rather uninteresting. Let's get rid of mod 1 because I don't think mod 1 is going to show us anything. Let's say mod 4. Okay, so this is saying if n goes to n and n plus 1 mod 2, that means that we can always go from 0 to 1 and back again. So that means we can have a connected object. So I think what we should do is plot this together with the corresponding nest graph. Okay, so hold on, let me do this. So I want to plot let's plot the combination. Let's say nest graph of this thing here, a(n) plus b, and we want to do that. Okay, let's do this. N function that, and then we want to say start from 0 and go, let's say, 5 steps. And now what we should see here okay, let's try this. All right, so this is showing let's go more than 5 steps. Let's go 10 steps there. All right, what is this showing us? So this, I think when this is a connected graph, that is when things can rejoin again. Oh boy. Well, so much for that theory. Look at this case here. This is saying, basically, we're starting with 0. And so this is saying that we can only reach even numbers in this picture. Does that make sense? Because we're starting, numbers that are equal to 0 or 2 mod 4. Does that make sense to people? We start from 0. We start from a number that is 0 mod 4. And so we wind up going to 2 mod 4, but nothing else. We can't get to 1 mod 4 in this case. Make sense to people?
Yeah.
Yeah.
Yes.
So my question then is, what is the criterion, given that this is n goes to, how do we work out, just by looking at those numbers a and b, how do we work out what the structure of this graph is going to be? Is that some simple number theoretic question? So that graph is telling us, as we look at, it's remarkably diverse actually, that graph. I have an urge to try just a few more cases here. Let's go up to, let's say, let's just go up to 4 for each of these. Whatever, it's going to generate a bunch of pictures. And I probably should have done a parallel table there. Okay. All right, so this is, boy, they all look the same. Where are the ones that just look like ordinary trees? So, I mean, something like this, we're starting from 0, and we can't get to 1 and 3, but we can get, it can recirculate around there. So it's kind of showing us a map of what values we can get to. Now, in a case like this, I'm very confused, because this is saying that starting with 0 mod 3, that's saying that 0 mod 3 maps only to 0 mod 3. So how can that be? So n goes to 4n. So let's take that case as an example. Okay. So where did I have some place to put this? Well, not here.
Are you initializing at 0?
Yes.
Well, then you've got 4n, so you'll only ever reach evens, and 3 plus n, so you'll only ever reach mods of 3, well, the same mods of 3. So
excellent. Yes, I think. Wait a minute. So let's check that. So okay. So I was wondering, if we initialize something other than 0, we will probably get a more interesting result. All right. Let's try rerunning this whole thing, initializing at 1, because that may produce generally more interesting answers. All right. So where were we initializing anything? There. It is, by the way, always remarkable that you can have a system like this that looks so simple, and yet it can be a bit non-trivial to analyze what's going on. Okay. So let's see, where was that case? Still looks very much the same. Maybe it's obvious that it has to be the same. So in this case here, was that our case here? 4n, 3 plus n? Oh yeah, but once it's at 1, 4n, 3 plus n. Okay, let's just do it and label it. Okay, 4n, 3 plus n. And this is probably going to be obvious. Okay, how obvious is this? Not as obvious as one might like. All right, let's say we label it with the labels mod n. That might make it more obvious what's going on. So let's say with g equals that graph. Graph g, and then we'll say vertex labels arrow, and now we want to name these vertex labels. So we say vertex list of g, and then we want to say thread, I think. Well, actually, one way we could do it is just say hash goes to mod hash comma 3. All right, let's see if this works. Okay. Very trivially, this is saying mod 3, everything is equal to 1 mod 3. Is that totally obvious? If you start off with, okay, so n plus 3 is going to preserve the same modulus. Is 4n, does 4n always preserve the same modulus? So if you have something, if I have something of the form 3u plus v, and I then say times 4 times that, right? Expand that out, 12u plus 4v, and so, oh, that mod 3 is always equal to, is that obvious?
0 plus 1.
Oh, yes. 0 plus, why is it plus 1? Why is it for 4v? I guess we just make a table of mod. This is completely obvious, I suspect, but let me just be stupid and do it explicitly. No, it's not so completely obvious. Why is that plus 1? Because the v, See, what has to happen is that we know it started as a +1, but this is preserving it as +1 for some reason.
Mm-hmm.
And so anything of the form 3n plus 1, if multiplied by 4, let's just do table 3u plus 1, u goes up to 10, and then let's say 4 times that, and we say that mod 3, and apparently the answer is always going to be 1. And it is, and there's probably an extremely elementary proof of that fact. Who can see that proof? Oh, because 4 is equal to 1 mod 3. I think that's why that's the case. But okay, so what we're seeing here is that, I mean, I'm a little bit surprised that we're not seeing, because I thought that up here we saw cases 2n plus 1, 2n plus 3. Why are we not seeing? Oh, I see, because we didn't have this a multiplier here. We didn't look at the cases where there was a multiplier here. That's why we're not seeing these other things. Let me just look at that case here. Well, let's just do the same exact thing. Let's just compute the same, because that was a nice diversity of different behaviors. So let's compute the exact same thing, and let's make that include framed of this thing here. And that was equal to, I see. So the question is, what value of k should we be using here? What value of the modulus should we use? Because that's not determined by these coefficients a, b, c, d. If I'm making sense. Right, so we could try, for example, let's try doing with k equals 3, for example. Let's see what that picture looks like. Okay, so with k equals 3, we're not really seeing anything particularly notable. I mean, these are just, this is showing us things about what moduli we can reach, but I'm not sure why we care about that. Let's try k equals 2. That will be the even odd question for these things. Okay, what on earth do we learn from this? I mean, that just doesn't seem to really, this doesn't seem to be giving us any information. I mean, it's not showing us why this one, for example, is different from this one. Well, so the question is, can we figure out why is 2n plus 1, 3n plus 2 a grid, but yet 2n plus 1, 3n plus 3 is a tree? Right? What is the criterion for when those branches rejoin? See what I'm saying? So that's the question here. 2n plus 1, 3n plus 2. That one makes a grid, but yet the one right next to it makes a tree. Right, so this one here makes a nice grid. Yet, oh, that's so weird. I just changed that to that, and I'm getting essentially a tree. Why? So I had thought maybe this modular arithmetic thing would give us an answer because it might tell us why these things can't ever rejoin. But that appears not to be the case. So who's got an idea for what might be going on here? 2n plus 2. Contrast the 3n plus 1 and 3n plus 2. 2n plus 2. I think we have a 2n plus 2 case here. We can try that in this case here. Come now, everybody, we've got a bunch of bright people here. Somebody's got to be able, just because I can't figure this out doesn't mean nobody else can figure this out. Ed, do you have an idea?
I'm looking at something with complex. You are really bright, though.
That's not what I need to hear. That's
Barbara just pasted in chat as well.
Yes, 2n plus 2 plus 1, 3n plus 2. All right, 2n plus, what are you suggesting? You're suggesting, just you can just say, what you're suggesting, 3n plus 2. Oh, you mean 2n plus 2, this case for 2n plus 2. Okay, well, let's try that. That gives that. And then the case for 3n plus 2. So the question is whether 2n plus 2 gives the same 3n plus 2. No. 2n plus 2, again, breaks that grid. But at least I feel better that I couldn't figure this out instantly. But I'm disappointed that we can't get this.
It's a nice candidate for more simulation, I think, though.
Yeah, I mean,
what emerges through different configurations.
Right. I mean, look, I think the point here, I mean, the thing is, to me, I'm surprised that this isn't a case where one can use number theory basically to solve it. I'm surprised that this gets, I'm always surprised by, the computational animals are always smarter than you are type thing. This is already something that's producing pretty complicated behavior. But I'd also like to know, like even in this case, right? In this case, the question would be, does it, I mean, let's go to 10 steps. Is it going to make look at that thing. I mean, is it going to make a tree, or are there going to be branches that join even after long periods of time? So for example, here, if I say layered graph plot, of that with an aspect ratio of 1/2, let's say, okay, so what we're seeing there, it's mostly a tree, but it has these few connections. These are sort of some few random number theoretic coincidences, presumably. And the question is, is this, so what must be happening is in some cases, those number theoretic coincidences are frequent enough that the thing just makes a grid. In other cases, they're really not able to withstand the treeing of the thing. Let's see. Nick is saying compare these. All right, we'll try that. Compare, expand 2 times 3m plus 1. Yes.
So this rule produces a grid, and the second one is not. Yeah, I will add this last one.
What are you saying? You're saying if you iterate the rule once, or what? Or are you saying if you?
Yeah, if you try to substitute one rule instead of another, you like get a similar thing,
Right.
independent of each order you do. So we get 5 plus 6 independent of the order. So we get a simple rule.
I see. I
like
see.
a grid.
I see.
And for the second one, you know.
Right. Okay. Fair enough. Yes, I had. Okay. So in fact, I had looked at that a little bit. Someplace here, I had this notion of index identities, right? So what you're saying is that F2, F1, F2, F1, et cetera, et cetera, et cetera. In one case, F1 and F2 commute. In the other case, they do not. They're
yeah.
Okay. So maybe what we're seeing here, we could think about this in terms of some commutator and some failure to commute. So you're saying in this case here, those two rules. So you're saying if I say, if I ask the question, if I say F1 equals 2 hash plus 1 and F2, well, let's see, what's the best way to do this? I mean, we can literally just, okay, let's do it this way. So we can say, that's n. So we literally just put this in there.
Yeah, if you just treat both pieces of this pair like a functions, you just make a commutator function, commutator of them.
Okay, well, let's do that. Let's write that as commutator of, let's say, F1, F2, and boy, just a little bit messy with that n there. Well, okay, let's do this. Let's take the commutator of the whole function f, and let's assume that that function f has, so what we're going to do, we're going to apply it to some variable x. So f of x will give two results. And now what we're going to do is we're going to say,
first of that.
Yeah, first of this. That will give us the first one, and then we want to take that, and then we want to say f of that, and we want to take the second element of that, and we want to compare that with the commutator the other way around.
Mm-hmm.
Okay, so let's take this now. Okay, and now we want to just say full simplify of that. And as predicted, that gives that. Okay, so now let's look at this commutator here. Nice, okay. All right, we're getting somewhere. Okay, well, probably we don't want full simplify, we might just want to expand here. Okay. But now what must happen, what must be happening is, for these, there are identities. So this is asking, to get a grid, you have to have the commutator vanishing. This case is some F1, 2, 2, 2, 1, or something equals F2, 1, 2, whatever it is. Every time these things merge, that's essentially an index identity, if that makes sense.
Yes. So
now the question is, can we compute when there is an index identity? So in other words, given these two functions, because not guaranteed that it's a fixed number of the number of indices going one way is the same as the number of indices going the other way. But the question is, how common is it? I mean, this reminds me a little bit in number theory of those things like what is it? Is that the ABC conjecture, or is that some other thing where you're asking, like in number theory, you might ask the question, when is 2 to the n equal to, Ed, do you know what I'm talking about?
Yes. For example, one example is 2 to the third plus 1 equals 3 to the 3 squared.
2 to the third, what?
2 to the third plus 1 equals 3 squared. 8 equals 9. And the question is, when are powers close together or at a difference, which is also a power, especially high powers?
Right. So is that related to this, do you think? I mean, it looks somewhat related.
I don't think so, especially, but it's weird when coincidences happen in number theory, which is basically another aspect of the ABC conjecture.
Right, but I mean, this is basically asking for coincidences. This thing here, where this joins, is a coincidence.
Yes, but with addition, those can be expected.
This isn't addition. It's got multiplication in it.
Look.
Look, there's multiplication and addition.
It's right? Still linear, though. It's when you get to the higher powers, like Fermat.
Well, okay, so if it's expected, Ed, tell me when it happens.
Oh, well, that's Collatz.
No, it's not, because this doesn't have a choice function.
You're still asking for the complete behavior. If you do Collatz without choice, you run into the same problem.
Okay, let's see that. Let's see that. So what is Collatz without choice?
2 n 3. Oh, my dog.
Is that? I don't think that's right, because it's not 2n, it's n over 2.
Stephen, did you see the chat from Phil?
I did. I think he's doing the same thing we were just doing, actually. Yeah, he's doing the same thing we were just doing. So Ed may have been eaten by his dog.
There's a lot of people in our local neighborhood setting off fireworks. So if his dog's anything like mine, they're not happy right now.
Why are they setting off fireworks?
Because they have nothing better to do. Oh.
What is this? What? Okay. Okay. So what is this showing us? Ed, what is this? And what's that sequence weirdness doing? Ed? I don't understand this at all. I don't understand what this is doing. What is that?
Posted something else to chat.
Yeah,
basically,
Ed, could you explain what this is, please?
It's basically the reverse Collatz conjecture, starting with 1. What integers do you reach? And basically, the answer
let's understand this. Let's understand exactly what you have here, okay? Because it's very similar to what we're looking at. But let's understand exactly what this is, okay? What is that sequence at thing doing?
Oh, that's just if it's not an integer, throw it away. That makes it much. That lets you go a lot further. I'm
sorry, I'm totally confused here. This is, why don't we just say nothing instead of that weird thing there? Right, if I'm not mistaken.
I wouldn't go 30 steps with that. Okay, that works.
Okay, so let's understand exactly what this is, Ed. Okay, so this is saying, given, I mean, this is an interesting object, and it's interesting how similar it is to what we've got here, right? But I want to understand it very precisely. So if I were to write this out in terms of a mod function instead of the integer q, right, what would it look like? Did you understand what I'm saying? So in other words, I say here, rather than if integer qn minus 1 over 3, I just say n. How do I get this? This is n minus 1 over 3. Do you understand what I'm asking?
You can definitely use mod instead. I'm not sure what it'll do.
Well, I'm trying to get a simpler form of this so that we can understand the more general case. Right?
Well, for colats, you basically need this form.
No, you don't. Colats has two choices. It has an even and an odd case, right?
Right, but if you want to see everything but avoid fractions, you need to throw out the fractions.
I understand that. So we can throw that out by looking at n mod. Okay, so you're saying the mod is equal to 1. So this is just saying here, the only point here, I mean, that's not getting us very far, but that's getting us somewhere, right? So that's the case you're saying that's equivalent to this, right?
Right.
Okay, so now let's simplify it further, right? Because what I'm trying to do is I'm trying to write this expression in terms of not, let's see, n minus 1 over 3. Let's think about this. So this is saying for any n, double it, if n is equal to 1 mod 3, if it's equal to, yeah, what are the simpler cases of this? That's what I'm trying to understand. Because this is, you're saying, okay, so if I take, this is the collat's problem going to what? Going to 1 or what?
Starting with 1 and seeing what numbers it hits.
No. It's not starting with 1. It's ending with 1. Right? That's the point.
No. For the reverse, you basically start with 1 and then try the operations in reverse.
I know. But that means the collat's problem is ending with 1. Right? This is.
Yes.
Okay. So this is. So if I label these. Okay, so this is saying, so there's normally a cycle, right? This is the cycle for the end of the collat's problem, right?
Right.
What is that cycle? That cycle goes 1, 4, 2. Is that right?
Correct.
And 0 is an absorbing state.
Correct.
Okay, so this is saying that 13 would lead directly to 4. How can that be?
The opposite. For regular colats, you reverse it. So 3 times 4 plus 1 is 13. 3n plus 1.
Yeah, I understand that. But so what are you saying here? You're saying that but normally everything attracts down to. So if we do the regular collat's thing, okay? So how would we do that? We would say, what would we do? To get regular collat's, we'd say nest graph of n goes to.
Yeah, you got it.
If even q of n over 2, otherwise 3n plus 1, right? But now I want to do that as a nest graph because what I want to do is I want to start from a whole bunch of values, if I'm not mistaken. Is this the right thing to do? Do you understand what I'm doing here?
Yes.
That's right. Oh, I want to go more than 4 steps. Okay, this is the right thing, I think. I want to go like 20 steps or something. Okay, so what this is showing is how things evolve to, so I want to say here, So the claim here is that everything evolves down to, it evolves through 10 down to the 142 cycle, right? Yeah, it's the same. Right, right. It is because everything has reached, right. So the collapse. Ed, did you understand? I mean, this
Yes.
is
Yeah.
okay. So now that should be. So your claim is that it's the same as this picture, but it doesn't look the same as this picture because this has a loop in it. And is that because I've reached larger values here? So the claim would be if I go to larger values here, let's say I go to 100 here, and I go, let's say 40 steps here. Okay, so this isn't enough, right? Because the Collatz problem claims that everything evolves down to the value. So let's say I go 400 steps here.
Right. My reverse thing isn't quite the same because if you have a even value, you can still do 3n plus 1.
Okay, well let's take a look. So this is the main Collatz thing. So this is a tree representing. So I don't know what that. This represents a very long sequence necessary to get to the origin. Correct?
Correct.
So what we could do in this picture is just for fun, we could plot, for example, in the y coordinate or something, we could plot the actual values, right? So we can see the thing going up and down.
Mm-hmm.
How would we do that here?
Extract out the edge list. And I get maybe find path. I'd go to OEIS and let's see.
Well, let's look at what happens if we just go. I'm just curious. If I go to 200 things here, I see. So that I didn't realize it was such a stringy object. The going to going to the origin here, right? So in other words, it's saying, now if I were to say, right, so I mean, the 3n plus 1 problem is basically saying that this is a connected object, correct?
Correct.
But the connectivity is a little bit difficult to determine because it's got such a long, let's try 1,000 of these, and let's say 2,000 steps here to make sure we're not messing something up here. Wow, it's kind of interesting. Have I seen this picture before? I don't know whether I've ever seen this picture before. Okay, so anyway, that's the tree of the forward Collatz problem, right? Now, you're explaining to me the reverse Collatz tree. So this is a pure attractor. Everything is being attracted down to this 412 cycle, right?
Correct. Uh-huh.
Okay. So let's understand. So what you've got up here is something different. What is this up here?
Right. That one, it isn't purely a choice function. You basically can go different ways with the value. So you could either multiply by 2 or divide by 3, and sometimes it wouldn't be the normal Collatz operation.
Okay, so wait a second. So if we were to do the forward version of this, what would it be?
I actually don't know.
Well, let's look at it. Let's figure it out. So what you're saying is n goes to 2n, which is the analog of n over 2, except that I mean, normally we would say if it's even, you divide by 2. Otherwise, you do this operation here. You do the inverse of this operation here. So in other words, the statement of the Collatz problem is the object is always connected. What is the analogous problem here? Is it that there'll always be a loop somehow, or what?
I don't know. One thing you can do though is if you look at the collapse graph you got later, 31 is a faraway point. So if you find the path from 1 to 31, you'll get one of these long strings.
Okay, well, or from 31 to 1 more accurately.
Right.
Okay, so find shortest path in that graph from 31 to 1. Oops. Okay, so that's a path that goes through some high values.
Right.
Okay. So somewhere in this picture, so if I were to look at that, do I say path graph of this? Is that right, Ed?
I think so, yes.
Okay. So that's the spine, so to speak, that takes one from 31. Presumably it's going there.
Yeah, that looks right.
Actually, if what I were to say 142, it'll look better if I say subgraph. A little bit better. All right, so that's an example of a path. Presumably it goes from that branch down there. Well, I don't actually know which direction it's in. Okay, fair enough. All right, so what's the analog in this previous thing here? All right, so let's look at this one here. So we can look at, okay, we're comparing basically this here to this here, right?
Right.
So 13 leads to 4 there. Where's 13 here? 13 is right there. And 13 in no way leads to 4 in this picture.
But it should be there.
What should be there?
Oh, right. Because 4 is even, you divide by 2. In this case, though, it doesn't matter. It always takes the 2 choices anyway. So even though 4 is even, it's multiplying by 3 and adding 1. So this is a path that's not taken by regular collats.
Okay, so you're saying that the regular collats is a subset of these paths. Is that
Yes,
correct?
Right.
Okay, what subset?
Basically, just like that. We would basically if the ending node is even, we would remove that path.
The ending node is even. Well, I don't understand. These paths.
If it's going odd to even, we would remove it.
So you're saying for any edge, if I get an edge list from this, right? You're saying if I take the edge list for this,
Mm-hmm.
okay, and what do you want me to do?
Select those where the first value isn't odd even.
What isn't odd? What do you mean the first value?
So that it's not the case that both the first value is odd and the second value is even.
So in other words, you're saying select the case where not, and what is it in terms of XOR?
I don't know.
Well, okay, but so you're saying it's this, right?
Yes.
Okay. And so now you say I make a graph out of those.
Right.
Okay, what the heck is that? Doesn't look like any of these. So let's take, look, let's do this. Let's take reverse of that, select this, take that graph with vertex labels. Okay, I don't understand this at all.
Let me take a look at it offline.
Okay, it doesn't seem right. But the main point you're making, which is a very interesting point, is that the problem that we're trying to solve, namely of when this thing here, 2n, 3n plus 1, okay? Your claim is that the coincidences there have something to do with the Collatz problem, right?
Yes.
Okay, I want you to figure out what they have to do with the Collatz problem, because I mean, in other words, in a sense, what's happening is any given, it's a set of two ends, and it's a sequence 1 2 2 2 1 1 1 whatever. Just like in the standard Collatz problem, if I'm going down this path, I could color each edge here with whether it's an even edge or an odd edge.
Oh, I just realized something else. This is related to something else in NKS where you looked at the complexity of integers and which ones could be built out of things like add 1 or multiply by 2.
Yes,
and you have
that's true.
And you have a plot of the different graphs.
I'm not sure if I had the graphs, actually. I'm not sure I had these graphs, but let's
not these graphs, but you had the complexity of say 17.
Yes, that's a good point. Okay, building integers from operations. It's just amazing how these really simple things end up just spiraling into such complexity so quickly.
Mm-hmm.
Okay, so let's see. I had systems based on numbers. I seem to remember that it was in my section on, I'm trying to remember where I had this. It was in a note. Nested digit sequences. Do you happen to remember where it was, or what on earth I can look for in the index? Reconstructing initial conditions, the 3n plus 1 problem. Reversible 3n plus 1 system. Huh. That's kind of interesting, because that the fact that it's reversible suggests, doesn't that suggest that we should be able to run it both ways?
I would think so, yeah.
So this is the reverse. And that comes from that page.
You should track down whoever wrote this book. He seems pretty smart.
Who knows? It's probably 25 years ago this was done. That particular page, actually probably more like 30 years ago. Okay, wait a minute. Where is this thing? Come on. Why did I have that? All notes for this section. Where would I have had that piece about? I mean, I remember this. I'm just completely forgotten where it is. Come on, where is it? Boy. Help. I think maybe I used bitxor in it. Maybe I put that in the index. If we're lucky, it will be in the index. And representing integers, 916. Good, good, good. What a crazy place for that to be. Crazy place. Whoever wrote this book was just trying to stuff random facts into the notes in the book. Okay, so what this was, let's take a look at this. 2a plus b minus 1. Oh, wow. You're right, Ed. This is very analogous. So this is a tree. What is this doing? A plus b, a times b. What is this doing? Do people understand what this is about? This is making a tree, making all possible trees, and then evaluating the tree by saying that the nodes of the tree are given by this operation in terms of a bunch of ones so for example, here I would be saying, in a sense, I'd be saying something like this. I'd be saying groupings of table of a bunch of ones, let's say 8 ones, with a function f with 2 arguments. Okay, and now the claim is that if that function f is, for example, 2 times hash 1, f goes to 2 times hash 1 plus hash 2 minus 1. That miraculously, if I were to take union of that I would get, oh, I see. The claim would be if I do that for all values, so let's say n there, table of that, let's just use this function as the thing here. So the claim is that this going up to n equals, let's say, 5. So eventually I will get every number. That's the claim here. That makes sense?
Right.
I don't know why it's true, but I claimed that. Why is that related? This is saying this is a tree. Let's understand what this is. So this is a tree. So this groupings thing, how do I display the groupings thing as a tree? I guess what I do is I just say expression tree of that. So this thing here, let's say I say 5 here. Then if I say expression tree, expression graph, those are all the trees that correspond to those possible expressions. Each one of those trees can be evaluated by putting a 1 at every node, at every leaf, and then using that combination function to sort of, actually this is interesting for studying combinators. I should look at this for studying combinators. Because this is a way of mapping any tree to a value, basically. And 2 different trees might map to the same value. But it's a way of mapping any tree to a value. But I don't see a direct relation to this. All right, well, okay, so look, the main takeaway from this, which I think is interesting, is the relationship to the Collatz problem. And you're sort of convincing me that I shouldn't be as embarrassed as I was, that I couldn't figure out what's going on in this case.
Right, because the behavior of whether there's a certain loop just with the simple Collatz, whether there's any others is one of the hardest problems in mathematics.
And it just doesn't, what's really interesting though, is that usually in studying these kinds of simple program type things, it's not easy to relate the hard problems in that case to the hard problems in traditional math. So if there's a relation here, that's really interesting.
Mm-hmm.
Right? I mean, it's kind of a little bit scary if there's a relation between what is an incredibly trivial version of this multiway. I mean, this multiway system based on numbers is even simpler than strings, which is even simpler than hypergraphs. And so these questions about merging and causal invariance and so on for hypergraphs, which is what we need for understanding quantum mechanics and so on, the fact that it's hard to figure out what's going on, even for the trivial case of numbers, and that's related to a sort of high problem in mathematics, gives us a sense of how difficult the mathematics for the physics case are likely to be.
Right. If we had an exact way of figuring out how the mergings occur, then we could apply that to the Collatz problem and solve it.
Yeah, well, fair enough. Okay, but maybe this is a generalization in some way of the Collatz problem. Is it?
I would say it's actually a harder problem for figuring out exactly how things merge when you've got these choices.
Okay, what do you think of my modulus idea?
Oh, I think it's a fine idea. It's one
it doesn't seem to get anywhere. I mean, in other words, it's just telling us that we can color these nodes. I mean, maybe I should just do that explicitly. Color the nodes by their value mod 3 or something. But it may not be very useful. I mean, this is saying right, that's an attempt to put order into this picture. But it's not really helping. Okay. All right, well, let's look. I can tell you some other things I figured out here. I just can't believe that this case is already such a mess. Okay, this was an attempt to make an actual Collatz thing. If even q of n over 2, otherwise 3n plus 1. Okay, that's the actual Collatz problem, if I'm not mistaken, right, Ed? Ed, are you with us? Hello, Ed. He's been eating his dog again.
Yeah, you're right. I was looking at GL3N and 2N. There is something you were looking at 4 years ago, I believe.
But Ed, why is this here not the correct generalization of 3n plus the correct 3n plus 1 picture? This is saying n goes to, if it's even, n over 2, otherwise 3. Oh, I see. Oh, no, I just added an arbitrary, just for good measure, n plus 1 here. See what I'm saying?
Right.
Now, the other case that I had started to look at was the case where you add a mod. Yeah, these cases here where you're saying okay, so in this case, what is the relationship between this? Okay, so this is mod, something like this, okay? So that's, again, another Collatz-like thing, I think, or maybe not. Right, that's adding. See, now I'm curious, if I take this mod for different numbers, A and B, here, let's see, I wanted to say table that A goes up to 5, B goes up to A, I think, because I don't need any, there's no point in going it the other way around. Oh my gosh, look at these crazy creatures. Okay, and that has 157,000 nodes. Let me bring that down to 10 or something. Oh gosh, look at this stuff. It's just crazy. Look at that thing. What is that thing doing? You know, I'm sorry, it just reminds me again of this mantra, the computational animals are always smarter than you are. And also these look bizarrely similar. Oh, I see, there's a 2 mod, whatever. I wonder what these look like. If I don't put the 2 in there, if I just say mod, what is that going to do? What's this going to do here? Oh my gosh, even that isn't trivial. How can that be not trivial? That's just bizarre. Look at this thing. What the heck is going on there? So this is looking at the case where you are saying for every, this is just linear except with mods. So that's 1, 2, 3, 4. 2. So that's saying, let's go like 30 steps here. Let's not go 30 steps. Oh, is that thing periodic, I wonder? Let's try going up to like 7 or something here. What is this doing? What is this doing? Okay, so that's 7, 2. Oh my gosh, this is just so crazy.
What happens if you label those points?
Yeah, I will. Okay, so I'm sure what happens if I go further here, I mean, it's making this weird snake. Is the snake periodic?
And we can take a look at the vertex list and see where it starts, where if any values stay missing, or if it eventually hits everything.
But do you think it's periodic?
If it hits everything, yes, eventually, after some Frobenius-like value.
Okay. But so you're, okay, so let's just do that. Up, that's not what I wanted. That's not what I wanted either. Okay, there we go. Okay. Let's just say, well, it is sorted.
And complement range 125 that.
That's plausibly reaching over value, because it's probably got, let's go up to 40 steps or something. That's really weird, because that's not Frobenius-like, in the sense there doesn't seem to be a finite length of that. Oh, but there is. Okay, explain that weird number theoretical thing. Oh, but no, the 125. Oh, it's only going up to 125, so we don't know how much it goes. You got what I'm saying?
Right. Yeah, try like 300 or something. Okay.
But so there are values here that we're just not reaching, however high we go.
Oh, let's do something equals that vertex list and then complement range max and then the thing.
Okay, wait a minute. You're saying
Put that above.
so vertex list is that. Okay. And then what?
Complement range max VV VV.
Oh, let's just do this for arbitrary. Okay, and now we can try that with up to a larger value. Okay, what are those numbers, Ed?
I don't know.
Let's do differences on them. Oh, how fascinating. 7 times 2 is 14.
Oh, right. The tail, it will eventually hit everything, but the tail will miss some values because it's not wrapping around correctly.
I don't think it'll hit everything. This is saying it doesn't hit everything. The numbers mod 14, that's missing a bunch of numbers mod 14.
Oh, right. Those will be the only ones missing in general. It'll hit everything except for those.
I'm not worried about the
values.
tail. The tail, I understand, is going to go away.
Mm-hmm.
So it's got a Frobenius-like phenomenon, and then it hits everything, other than the multiples of 14.
Correct.
And the multiples of 14 doesn't hit because why?
Multiples of 14 mod 14 some value. It might be +3 or something. Who knows?
Okay, so your claim is that if I do this computation for other values of A and B, okay, so let's try this for A, B here, that if I do this thing for table of that with A goes up to 7, B goes up to A. Actually, why not I do parallel table just because it'll be faster. Whew.
It's the numbers that are equal to 7 mod 14 in that case.
Okay. Should I do differences in all these cases?
That looks suggestive.
Look at that last one. Look at that last one. Is that periodic? Yeah, that is periodic. Yeah, those are periodic. Okay, so fortunately, this creature was not a completely unruly object. So this case here is understandable and eventually hits everything, but with some slight exceptions. But the question is this analogous to the Collatz case or not? And I noticed that Barbara put in the chat the result of Conway's, which was actually a it's also, there's a version of that in the NKS book actually, in kind of an interesting version, I think. That has to do with this case here. I think it's this case here, where I'm looking at simulating cellular automata and so on with generalized arithmetic sequences. How do I do that? Someplace here. But yes, you can get an arithmetic. These arithmetic sequences can be undecided. You can get universality. That's the main point. Where did I have that? I was sure I had that someplace here. Right, but yes, that's absolutely correct that you can have. Is that it there? Nope. I don't look at this particular section very often. For some reason, this is one of these sections where, yes, we proved that you can emulate a cellular automaton. Yeah, I think this is the right case. Oh yeah, arithmetic sequence can emulate a register machine. That is the right case. That's the case. That proves universality for a simple arithmetic system. And actually, I should be reminded of, that is a good point, that's a case where, what is that showing? I mean, we could do the analog of the Collatz. That's an interesting idea. Universal arithmetic system. Although I'm not sure that that's definitely not the right thing there. So in this system, this is a generalization of Collatz where instead of where we are giving mod 30, we're giving what to do for each value mod 30. So in the case of Collatz, it's just mod 2, and we give the value, but here we're doing it mod 30, so we've got lots of choices. Oh gosh. Right. But I don't know what that's going to look like actually, because so this is a case. What does it mean that what does it mean that we can get universality? I'm not sure. It raises the question: what's the simplest universal multiway system, or multiway system with numbers, for instance? Okay. Let's okay. We should probably wrap fairly soon. We were looking at complex numbers, and we were making, I mean, this was another thing we were looking at here, was this dimension thing. That surprised me a bit. But now, you know, on the complex number side of things, where was that? Okay. I got these things. So, but by the way, this way of plotting with coordinates, is there a way to do that with just ordinary integers by taking them mod something or other, or in different bases or something? Is there a natural way to do it? Just like there's a natural way to do it for complex numbers, is there a natural way to do it for?
Yes, when we did that with mod in the 7 case earlier on in the same notebook.
Yeah, but what about in the case of, I mean, if I were doing that in for like that 2n+1.
Basically, you could just use that same code and pick any modulus you like.
I know, but I mean, what about this? Is this going to do anything interesting in that case?
It'll not look periodic. Other than that, I don't know.
Yeah, I understand, but I mean, does it have any particular significance to pick up? Because in the complex number case, there's no modulus being picked. It's just the actual complex numbers plotted in, you know, re-m.
Well, that's one of those good questions. I'm not sure anybody's ever tried that, so it might be interesting for an unsolved problem. So who knows?
Okay, well, let's do it. Let's just do that just for a second. Okay, so let's say mod. Is this mod? It's really it's quotient remainder plots.
Right.
Okay, so let's see. We had some code. I think I actually took.
Yeah, it's right there.
We go. Okay. All right, let's try this one, 2n plus 1. I predict this is not going to be interesting, but what on earth is that? What on earth is that? Let's get rid of the vertex labels. Okay, explain.
Let's try the mod instead of 7, like 20 or something.
Well, actually, why don't we try 2 to begin with? Totally boring. Okay, you think we should try, why don't we try, I'm going to try 2 to the n. What the heck is that? All right, let's try 2 to the 5. Okay, and let's run a few more steps. Okay, what is that? What is that? Those things look like the things from just multiples. What is that? What is this? What is this? What does this mean?
Huh.
Well, we can try some. Let's try some other moduli, just to see whether we learn anything from that. Let's just try making. When in doubt, try them all. So let's try modulus k, and let's try that table. Let's do. Well, let's just do a table. K goes up to 20, let's say. I would consider that fairly unilluminating.
Yeah, they all look crazy. But that's what kind of we were expecting.
Yes, I wasn't expecting this to untangle things. Is there any other decomposition that might untangle things? Like, for example, some kind of base decomposition or something. I don't see it. I don't see it. All right, let's have a quick look at complex numbers and then we'll wrap up. Although you've now convinced me that even though I thought this was going to be a trivial problem, that this is significantly harder than I thought.
Right, right.
You know, it is amazing that for 40 years I can make the same mistake repeatedly. That every time I look at some new system, I think it's going to be easy. Because I'm convinced that it just couldn't possibly be another example of the same phenomenon that I've seen for 40 years. Oh, well, okay.
Well, I had the same idea about the Hadwiger-Nelson problem and just played around with square root of 3, square root of 33 with variations of the Moser spindle and put up a big field of points close together. And Henri de Grey said, let's try adding square root of 7 to that, and he solved the Hadwiger-Nelson problem. I just needed to go a little bit further, and that would have been it.
Right. So, by the way, you are also pointing out that this same type of system that we've got here, we've also got the algebraic number case of this system, and we've got the rational case, which I don't think will be terribly different. I mean, in this case here, if I were to use algebraic numbers here, I think this will be a big mess. Oh, for goodness sake. How can that look any different?
Because square root of 2 happens to have special properties. Certain algebraic numbers, if they're related to Poisson numbers, will converge very nicely, like the plastic constant. But most other algebraic numbers will not.
It's the same for square root of 3 here.
Yeah, that also falls into that category.
Okay,
but
I'm going to put pi there. If pi looks the same, something is fishy here.
That's just multiples of pi. I was thinking more of multiplication.
Well, you're saying that an arbitrary. Okay, that's an interesting idea from Nick there. Okay, you're saying that this is saying that for an arbitrary c, that basically that c is completely, that's interesting, that this is completely undetermined, right? The c, it doesn't matter at all.
Right.
Is that obvious?
It is when you're just looking at because it's basically ax, or 2x, 3x, 4x, and so on.
Okay, now when that's square root of 2, though, it blows itself up, even though the powers of square root of 2 will be the same. So if I do that plus 1, those are not, they're never combining. Even though the square root of 2 squared, so to speak, done twice should be 2 times n.
Right. I think you might get more if you use -1 or something like that. And
look,
one thing
look, there is some merging there.
Right.
But you're saying there's only merging in a trivial case.
No, I'm saying that you'll get more merging with Poisson numbers.
All right, let me try a friendly Poisson number. What is a friendly Poisson?
Well, square root of 2 it happens to be one, and also the golden ratio, and the plastic constant. And this is something I was trying earlier. I wasn't able to get it to work well.
Well, here, first of all, let me just do. How do I do the simplify here? I probably
root reduce at the start. Over the whole thing, yeah.
Oh, and these maybe give different answers if I say root reduce here.
Yes.
Oh, for goodness sake. You know, these creatures are just too complicated. It's crazy. It's just crazy. Okay, that is not probably going to do anything in root reduction, but this will. It's just crazy. Okay, so you're claiming, so like that creature there, not very interesting. Okay, so your claim is that if I use something other than a Poisson number, so for example here, do you think, I wonder if this is causal invariant. Let's find out. I wonder whether the, let's see, starting from 0, 4 steps, causal invariant Q. Oh, this is so weird. This is so weird. Okay, let's try a different number there. Let's try something that isn't one of your friendly Poisson numbers.
Square root of 93.
Square root of 93?
Or some other.
Can we try a smaller one? How about
sure, 17.
Really? Can we try a smaller number that is
Oh, sure.
That may take it. Oh. That would be so weird if there's a number theoretic connection to causal invariance, which is what this is saying.
Square root of 5, I think, will behave differently, though. I think that should work, yeah. But if you use
Okay, so
golden
what about
ratio there, though, I think it'll be different.
what the heck is that? What did I do here?
I don't know.
What on earth is that? Confused we are here.
I don't see anything wrong there.
Well, I suspect that's a bug in the multi-way function system code, because I think if we just do nest graph here, that's fine and dandy, but so this, okay, so let's just look qualitatively at what it's doing. See that, I bet that thing is causal invariant, because I bet what's going to happen there, if I say layered graph plot, so what is the distinction between a Poisson number? Yeah, I bet that's causal invariant. So if we look at the corresponding result for square root of 5, that's really cool. Yeah, that thing is much less, that thing is I mean, it still has some cross connections, but there are many fewer.
Right, and that's just a guess on my part, but geometrically, the Poisson numbers behave much more nicely than all others. And that's why I was able to find all those results in tiling that no one found before.
Well, but I mean, that's with respect to, yeah, but so I wonder whether this is somehow related. Those numbers have various properties with respect to their powers, yes?
Yes.
I mean, it's like they have small polynomial, they satisfy small polynomial relations.
Right, and if you basically multiply them and combine them together in basic ways, you wind up hitting the same values over and over, which is very valuable in tiling problems, because basically you want things to act in a semi-predictable way, but not too predictable. That's why these make really crazy tilings.
All right, well, that's interesting as well. Boy, you know, I thought this was going to be like a totally elementary note that was just going to have some trivial features. All right.
No, one thing we haven't hit on yet is unique factorization domains.
Yeah.
I'm wondering if there's something, if we append like the square root of 5, and there you have 1 plus square root of 5, 1 minus square root of 5 times equals 6.
Yeah, I understand. But there are UFDs corresponding things for various algebraic extensions.
Right. So I'm wondering if there's a nest graph with 2 forks we can set up that will have a node that has 4 items coming in. Because all the domains we've looked at so far have had unique factorization domains. I'm wondering if there's a way of skewing things in square root of 5 so that it doesn't happen.
Well, wait a second.
And I was looking at that earlier, and I couldn't find a case that worked well, but I believe one will exist.
Well, you're saying if I were to look at this with, I don't even know which the unique factorization domains are, but if you're saying not with multiplication or with multiplication.
With multiplication, for example, in the domain Q square root of 5, there's 2 ways of factoring 6.
Okay, but so if I say 1 plus square root of 5 times n, And what are you suggesting?
2, but I tried this 2 times n.
Well, let's try 1 minus square root of 5, or square root of 5 minus 1.
Oh, well, basically you'd want to have, you'd want to set up both multiplications to be possible. So the other one would be 2n, and basically if you hit 3, you would hit 6 with the 2n branch, and if you hit 1 minus square root of 5, you'd hit it with the other branch.
You know, one of the principles of the animals are always smarter than you are is any attempt to construct something will fail.
Right, and I did spend about 20 minutes trying to construct this to get that to work. I'm pretty sure there is something weird in when you go outside of unique factorization domains.
Well, I don't quite understand why. Yeah, that's just a grid. It's just a 3-dimensional grid. Okay, well, look, I think we should probably wrap up here, but the complex number case, the thing of interest there, okay, so with real numbers here, is there a way of getting the leaves to eventually converge? See what I'm asking? Of
Yes.
getting the values to eventually converge. In other words, you're going to have essentially the sum of some geometric series, for example. What you want is the sum of 2 generalized geometric series, because you can think of it, you know, an arithmetic series. I mean, so a way to think about this is like, you know, these are kind of like arithmetic series or geometric series. So like this one that we've been looking at is a combination arithmetic series, geometric series.
Oh, for that first nest graph there, it should be 1 plus square root of 5.
Well, that's a whole different can of worms. Yeah, I don't know what that's going to do. All right, but you understand my question, Ed, that this is for the case where it's going to be real numbers here, right?
Mm-hmm.
The question is, well, I see. So the issue is there could be an infinite, even for real numbers, if they are finitely specified real numbers, algebraic numbers, for example, there could be places where they agree, but if you have arbitrary real numbers, that cannot happen. Am I right?
Right. Mm-hmm.
Even though in the case of the complex trees, I think it can happen. I think it's what Bernat is looking at, where he's basically saying there's an index identity. You see what I'm saying? It doesn't matter what the values are.
Right. I think his are related to special values in Julia sets.
Yeah. I'm just going to look at this one thing that Nick had sent us here. I don't even know what this is. Integer spectral decomposition. I don't even know what that is. Let's see what it is. What is this creature? What is this? 7 in mod. I have no idea what this is.
I'm guessing in Z5, 6 would have 2 different decompositions.
Everything seems to have 2 different decompositions.
Okay, I have no idea what it's doing.
2, 1, 3. Well, we need a base for the thing, so we need to know.
There's a function integer spectral basis. You can look in the properties there. Properties and relations, there is an example on how to.
Spectral basis.
But that doesn't look like a short exploration.
Well, it looks like an interesting thing, but we can just run it for this case. Let's just try it. You have an idea what the base should be here? So this would be intraspectral decomposition lag.
Well, it shouldn't be a prime because it's going to be just one coordinate.
No, this is going to give a pair of coordinates, right? For every number n, that's going to give a pair of coordinates.
It can give you more than 2. I think.
It can give more than 2?
It depends on your basis, or basis integer.
It's going to blow up then for some values here. Okay, so those are probably the cases where it fails, where it gives more than 2 values. So in those ones, we would have to plot it like in 3 dimensions or something.
Yeah.
Well, that's kind of interesting. I don't know what this is doing. Is this your function?
Yeah, it is mine.
Good. Okay, then you can explain to us what it does at some point. Okay, well, that might be doing something interesting here. It's hard to tell. I mean, it's very hard to tell. I see that's steps. It may also be the case that many values are being mapped to the same positions, which means that this looks simpler than it really is because the thing is really tracing a bunch of different paths. All right, well, we should wrap it up here. Well, Ed has convinced me that this is a more complicated problem than I thought, but we should not give up, and I want to produce this bulletin to at least explain what
one note you basically need to say is collapse is difficult.
Yes, but Ed, I want to see the exact correspondence. All right, let's wrap it up. Thanks a lot, guys, and see you all tomorrow. Okay.
Thanks. Bye, everyone. Get some
Bye.
rest.
Thanks.
Bye.
Thanks. Bye.